Okay, in this little lecture video, we're going to talk about the regulation of oxygen binding to hemoglobin. And that oxygen binding is regulated by a molecule that is one of the intermediate molecules produced and utilized during metabolism. And that molecule is 2,3-bisphospho, this is a long one, glycerate, henceforth called 2,3-BPG for short. So this type of regulation is called allosteric heterotrophic regulation. And we're going to cover this more in our in-class activity. Allosteric, meaning that the BPG binds to a region other than where the actual ligand binds. So it does not bind to the heme the way oxygen does. So BPG has a different or a separate binding site on hemoglobin surface. Heterotrophic means that the regulation is not by the same ligand. So if it were homotrophic, we know that there is some homotropic contribution to oxygen binding because it's cooperative. Heterotrophic means a different molecule is doing regulation. So 2,3-BPG is an example of allosteric heterotrophic regulation of oxygen binding to hemoglobin. So let's take a look at this molecule. So we've got, it's kind of a big one. I don't know why I don't turn my iPad a different way, but I'm already committed to drawing it this way. This should give you plenty of time to draw it too, so you can practice and take a look at what the molecule looks like. So whenever you see molecules and you know what they do, you should try and get a feel for what it is about that molecule that might be contributing to its function. So 2,3-BPG binds to hemoglobin. And if I were to ask you how this binds to hemoglobin, you should take one look at this molecule and see those 5 negative charges jumping out at you. And so this molecule binds to a positively charged patch of residues on the hemoglobin surface, and it binds tightly to reduce affinity for oxygen. So the binding of BPG reduces hemoglobin's affinity for O2, which means that this molecule stabilizes the T state of hemoglobin. So that T conformation, the tense state where we have low oxygen affinity. Okay, so here's a space-filling model of BPG binding to the T state of hemoglobin. So what this picture is trying to show is that we have two different states. And so right here, this is the positively charged patch of amino acids, and I'll try and show an up-close picture of that in a second. So what we have is BPG binding across the subunits, so those negative charges interacting with those positively charged residues. And what that's doing is you're creating all of these ionic interactions, and you're preventing the conformational change that would regularly take place when oxygen binds to its heme. So typically we know that when oxygen binds to the heme, that pulls the iron, which pulls the porphyrin ring, which pulls that distal histidine residue, which tugs on the backbone of the entire molecule, causing the conformational change to the R state. But in the presence of BPG, that conformational change can't take place. You kind of think of it as the BPG would be pulling it back. It's preventing that shift of the backbone. But you can see that when oxygen is bound to its heme, this binding pocket where BPG normally sticks isn't there anymore. So in the absence of BPG, we can have those conformational changes, and BPG does not have an affinity for the R state of hemoglobin. So here's a little bit of a different type of picture where you can really see those interactions taking place between the negative charges on the BPG and the positively charged histidine residues. So you can see this binding pocket crossing. So there's another one, here's another one, and here's another one. So you've got those histidine residues on these two hemoglobin molecules that are opposite one another. So this one and this one. Then you also see some lysine residues sticking out for some additional charge stabilization. So you've got a lot of ionic interactions taking place to hold this molecule in place. So the body uses BPG as a mechanism to regulate oxygen binding under conditions where the pressure of oxygen is changing. So, you always hear about, people are climbing Mount Everest, then they camp for a long time at different base camps, and people always talk about how they're just getting used to the oxygen pressure so that they can breathe better, because at the high altitude, low pressure of oxygen, it's difficult to breathe. But it's not necessarily the actual binding of oxygen to hemoglobin in the lungs that's a problem. It's that there's less oxygen delivery to tissues when you're at a higher altitude. Oops, I want to write in red. So high altitude has a lower oxygen pressure, which means there's less O2 delivery to tissues. And so what that means is that there's less oxygen being delivered to the tissues. We need a way to get hemoglobin to unload it better. And so what happens is the body produces more 2,3-BPG. So if we produce more 2,3-BPG, then we have more 2,3-BPG binding to hemoglobin, and we know that BPG binding to hemoglobin stabilizes the low oxygen affinity state. So it's going to encourage the release of oxygen in the tissues. It's not really noticed in the lungs at all, since the pressure in the lungs is higher. So we can look at that graphically using our oxygen binding diagram. So here's the pressure of O2. Here's the saturation of O2. So here's our regular curve. And so we can look at this as showing this is the pressure, let's say, in the tissues. Then this is the pressure, in the lungs at sea level. And then in blue, let's put the pressure in the lungs at a higher altitude. So that's blue equals the lungs at higher altitude. And so you can see from this graph that there's not much difference in the oxygen saturation level in the lungs, right? So if you look up here, there's not much difference. Probably even less if I could draw a better line. Okay, so under these conditions, we're talking 5 millimolar BPG in the body. So that's what our production level is. And if this is the pressure that we release it, and this is the pressure we bind it, if we're just talking about sea level, then we could say that the difference between those two, this amount, that hemoglobin is releasing about 40% of its oxygen. So it binds it in the lungs, in the tissues, then it releases about 40%. That's the difference in oxygen saturation between the tissues and the lungs when you're at sea level. However, when you're at higher altitudes, and maybe I didn't show this super awesomely, then we're looking at this difference here. And even though you can't tell from the way I drew it, I can tell you that this difference is now 30%. So at higher altitudes, your hemoglobin is now unloading less oxygen in the tissues. So to increase oxygen delivery back to its normal 40% amount, the concentration of BPG increases to about 8 millimolar. And what that's going to do is that's going to shift our oxygen saturation curve to the right. Something like that. So now that we've moved to the right, you can see that we've got a new saturation level. So this is at 8 millimolar bpg. So now that we've moved to the right, we've got a new saturation level of oxygen in the tissues. So now this value is back to a 40% release. So by increasing the amount of BPG present, we've now increased the amount of oxygen delivery once a hemoglobin gets to the tissues. And you should be able to look at this pressure graph or this oxygen binding graph and get a idea about the affinity of hemoglobin for oxygen in the presence versus the absence of BPG. We know that since we've shifted this graph to the right, that it takes more oxygen to reach the halfway mark, to reach the 50% saturation. So we know that the dissociation constant has gone up. So there's more hemoglobin and oxygen dissociated. So the KD is now greater for oxygen in the presence of BPG.